In this video, we're going to be looking at one of the skills that we need in order to eventually start to solve equations. So we're going to learn how to simplify polynomial expressions. Now, a lot of the time, people say, I'm okay at math, but once you start to bring in letters and numbers, I get confused and I don't know what to do. It's actually not that different than stuff we do in our everyday lives. So I want to give you an example. I've got some images over here that I'm going to move around, but I want you to imagine that you're in a grocery store and you grab 3 apples. Okay, so I'm going to take these 3 apples over. There's 1, there's 2, and there's 3. And you add to your grocery basket another 2 apples. You realize you need a few more. Well, you already know how to do this kind of math, right? Because this is going to give you 5. But 5 what? Specifically 5 apples. So we're familiar with stuff like that. What if we talked about, okay, we went to the fruit aisle and now we actually need some bananas. So let's say I have 2 bananas. 1, 2. And I decide, you know what? I need to grab 5 more. Okay, so did I print some extra? 1, 2, 3, 4, 5. And I don't need this one. Well, what do we end up in our basket? We now have, and you can count it if you need to, 1, 2, 3, 4, 5, 6, 7. 7, and again, we don't just say 7. You've got to tell me what you have. So 7 bananas. Whoops. Bananas. So that's, I think, fairly doable for most people. So when we talk about math with letters, we're really just doing more of the same. But instead of us having to write the word apples every time, why don't we give it a letter? Maybe just the letter A. So I could say I have 3 apples plus 2 apples. A is just our short form for apples because maybe we don't want to write the whole word. And so that gives us 5 apples. And so that's the kind of math that we're looking at today. If I add 2 things like this, what's my answer going to be? So we're going to look at this for the rest of today's video. Similarly, for the banana example over here, I'm going to move these bananas down. And what I have is, let's say I use the letter B. Whoops, that's not what I meant to do. Let's say I want to use the letter B to represent the number of bananas. I have 2B, or rather, let B represent bananas. So 2B plus 5B, so I have 7 Bs. So again, that's all simplifying expressions is. Except eventually, we're going to start using x's. So for example, I might do 2x plus 5x. Well, now I have 7 x's, but I'll get to that in a second. Okay, so I have this poster set here to kind of go over this whole idea of adding and subtracting expressions. So this is, again, I want you to think of it like our apples and bananas. But if I have a question like this, x plus x, I want you to imagine it, because now we're not talking about something concrete like apples and bananas. So let's turn it into something that's concrete. Let's imagine I have a wooden tile and it says x on it. So x plus x, we can think of it as we have 2 of these x tiles. So imagine that each of these x's is represented by a wooden tile with an x on it. We're going to count how many we have. 1, 2. Therefore, our answer is 2x. Now, on the other side, I'm going to compare it with multiplication, but that will be for a different video. Here's another example. So if I had 3 x's plus 2 x's, much like our 3 apples and 2 apples, I'm going to visualize that as 3 wooden tiles with x's on it plus 2 wooden tiles with x's on it. We're going to count how many we have, and therefore we have 5. So there's our statement there. Here's just another example where we're doing 3 x's plus an x. Now, by the way, you could also say there's just a 1x in front of it, but we don't usually write that. And it works the same way with subtracting. So if I have x take away x, the story I'm going to tell in my head is I have a tile with an x on it. The take away x means, well, I'm actually going to take it away. And so I have 0 tiles left, 0 of anything. So it's just a 0. And this is how we write that math fact. Last one, what if I have something like 6x's minus 2x's? Well, my situation, and again, you can think of it like apples. If I had 6 apples and someone took away 2 apples, I have 4 apples. So I'm still going to have that letter there. A lot of people think that this might become just 4 because the x's are gone. But if you think of it this way, you'll see why that's not the case. So 6 x's means I have 1, 2, 3, 4, 5, 6 different tiles, 6 tiles altogether with an X. Subtract 2 means I'm taking 2 of these away, and I have 4 left, but 4 X's left, so I have to have that X in there. There's something else that we want to introduce you to, and it's the idea of like terms. So let's say I had a new statement. Let's say I said, I've got 3 apples in my basket. I go and I grab another 2 apples. And in that same basket, I have 5 bananas, and then I go back for another 2 bananas. Well, how are we going to add this? Well, we can't add apples and bananas together, but we can say I can add these so that I've got 5 apples, and I can add these so that altogether I have 7 bananas. Okay, but we have to stop there because I can't add apples and bananas together. I mean, I could say that I have 12 fruit, but now all of a sudden that's a whole different thing that I'm talking about. So I want to introduce you to the concept of something called a like term. So a like term are things that have the same variable and the same exponent. So for example, in this question here, these are like terms. They're different from these, but these are also like terms of one another. Let me do this with more mathy terms. So I could rewrite this as 3a plus 2a plus 5b plus 2b. These are now what we call like terms. Okay, and these are a different set of like terms. So before I keep talking about this thing called like terms, let's just quickly go over what a term even is. So a term consists of generally a number and a letter, and sometimes that letter has an exponent attached to it, but let's not get into that just yet. So a term would have a few components. This big number in front we call a coefficient, and that's just a fancy word for the front number of the term. This bit here, the letter, is what we call the variable. And again, like I said, sometimes the variable can have an exponent, but we'll get to that a little bit later when we talk about different types of like terms. So when we say look for like terms, or these terms are like terms, we're talking about saying, well, this is one term here, here's a second term here, and because they have the same letter, because they're both talking about, in our example, apples, these are like terms. They're similar, they're like each other. Whereas if I took 2a and I compared it with 5b, these are each 2 different terms, but they're terms that are unlike because this portion here is different. Okay, so hopefully you're able to see what a term is. Basically, each term, if I've got it linked together with a number of different things, each term is separated by a plus or minus. So in this question here, if I don't simplify it, I'm just looking at the way it's written here, I've got 1, 2, 3, 4 terms. These 2 were considered like terms. And so 3 apples plus 2 apples gave us 5. 5 bananas plus 2 bananas gave us 7 bananas. And so that's how we did that. But again, this is just to clarify a little bit about what a term even is before we go into more depth about what a like term is and what an unlike term is. It's important to know what like terms are and what like terms aren't, because we're allowed to add and subtract like terms. We just can't add and subtract them if they're unlike terms. So like terms, for example, would be things like 3x and 4x, or even negative 6x, or just an x. Another set of like terms could be something like 2x squared, and something that's a like term there, it would have to have the same variable, so the same letter, as well as the same exponent. Okay, so I'm going to, let's see, I want to draw it kind of like a tile. So I'm going to put a square around this. So basically, for these like terms, they all have the same thing on the tile. Same with this, they each have the same thing written on their tile.
So it is important for us to understand what terms are like terms versus terms that are unlike from each other. And the reason is because we are allowed to add and subtract like terms, but we're not allowed to add or subtract unlike terms. So let me give you some examples. One's already written here for you, but if we have a term that says x, and imagine if you have our tiles, and then we have another tile with an x squared. Well, what's written on the tiles is different, so we would consider those to be unlike terms. So if I had a number in front, let's say a 3, that doesn't change anything. These are still considered unlike terms because one has an x on a tile and the other one has a x squared on a tile. Some other examples of unlike terms would be, for example, for y or versus, maybe I'll say versus for y squared. Once again, if you look at what's written on that tile, it'd be a y versus a y squared.
I do have a question for you though. I might have something like this and this. And my question to you is, are these like terms or unlike terms? So pause it, think through it. Yes, these would be like terms. And again, the way I would think about it is I'd have a tile, 2 tiles that say xy, 4 tiles that say the same thing, xy, 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 and therefore I now have 6 of those same tiles. So I'm going to go ahead and move these to my like terms section. Whoops. And let me go ahead and erase this. Now, if that made sense, I want you to put your thinking caps on and decide whether or not this and this are like terms. Now, they look very similar to the last example. This is the part that's different. So I want you to decide whether they are like terms or unlike terms. And my hint to you is this means multiplication. So this means x times y. This means y times x. Do those two things, are they the same or are they different? Okay, so hopefully you've had a chance to think through it. These are like terms. Okay, and they're like terms because when it comes to multiplication, it doesn't matter what order you put it in. So we may write like terms like, I'm going to do A's and B's, maybe 3AB and 7BA. It doesn't matter what order that goes in because it's multiplication. So now that we have a better idea of what like terms versus unlike terms are, let's go over some examples. Okay, so over here, this will be my part B, and we're going to just go over some harder examples here. I'm going to have 3, and then I will give 3 more to you to practice if you'd like. So if you have a scrap piece of paper, I would grab that. All right, here's my starting question. And the thing I need you to see is, well, we actually have a few different types of like terms here. I have the x's, but I also have the y's. So what I'd like to do first is I'm going to group them so all of the x's are on one side of my equation, of my expression, and all the y's are on the other. Now, when you move it, be careful because this 2x has a sign in front of it and it goes along with it. It sticks with it. So what do I mean? I'm going to show you this in 2 ways. So I'm going to collect my x's first, so that's this one. And then I'm going to collect my negative 2x, and then I'm going to do my positive 4y and my positive 7y. Actually, you know what? Let's change that to a subtract just to make it slightly more challenging. So then that will also be a subtract there too. Now, often we forget what signs go with it, so I'm going to show you this in a different way. Let's just move this off to the side so we can compare it. I'm going to duplicate this, and I want to show you what we're really doing. We are quite literally rearranging these terms. Now, each of these things is considered a term. Each term is separated by a plus or a minus. So we have 1, 2, 3, 4 terms. Now, I will say that when I move it, I do have to move it along with the sign in front of it. Okay, so if I wanted to group the x's together, I'm going to take this x and the 2x, but I need to grab the negative as well. And then, oops, looks like I'm missing a y here too, aren't I? There we go. And now, and it doesn't matter which one I put first. I could put this one first, or I could move this one first. I'm going to choose to move the positive one there, and then this one. And that's how I get that bit there. So eventually, you're going to be able to do that line a lot faster. Well, what am I going to do next? I'm going to do this. So 3x's minus 2x's. So now, our shortcut is we know our answer is going to have to do with x's because that's the thing that's on the tile. I just have to do the numbers now. 3 minus 2 is 1, so I have a 1x. And this tip is going to be really handy for this because I have 4y take away 7y. Now that's hard to imagine when you think of actual tiles or objects, but our shortcut is this. Keep the variable, and I'm just going to do the numbers, the integer part of it. 4 minus 7 is negative 3, so I have negative 3y. It turns into a subtract by the time it goes back into our expression. Hopefully that makes sense. Let's do 2 more so that you feel a lot more comfortable with it, and then I'm going to set you off to try some on your own. So I've got 2x squared plus 3x plus 1. And the first question I'm going to ask you after you copy this is how many different types of like terms do you see? How many different types of like terms do you see? Now, if you just have a pencil and you don't have a lot of colors, this is what I do sometimes. I've got an x squared like term family, and then maybe I'll use squiggly lines for the x's, and maybe I'll use just a different type of underlying for what we call the constants that have no variables. So I have 3 different types of like terms. I'm going to rearrange them, and we usually like to put the ones with the highest exponent first. So I'm going to copy this guy out, copy this term next, and again, remember to take that negative sign along with it. Now I'm going to take my plus 3x, my plus x, my plus 1, and my plus 2. And again, I like to underline, don't use brackets, I would just underline these to help you out. So when I'm trying to figure out this answer, I know it's going to have an x squared. I just have to do 2 minus 6 in my head. Okay, so 2 minus 6 is negative 4, x squared. For this one, I know I'm going to have an x, and then I have to do 3 plus 1 in my head, and if you're new, I would add in that invisible one until you remember it's there and you don't need to keep writing it in. And then finally, this last bit is pretty straightforward, and we get a 3. So this whole thing would be our final answer, and we have to stop there because these are not like terms and we can't go any further. Just like how over here, we had to stop at this step and this step because they're unlike terms and we can't go any further. All right, last one. Okay, pause the video, see if you can answer this, and then come on back. So these are considered like terms. I can very easily rewrite the yx into xy, and now it's a little bit easier to see. Now, if you're stuck, remember what would be on that wooden tile. It's xy that would be written on that wooden tile. So I have 2 of them. I'm taking away 3. Let me do the integers. So that gives me negative 1. Negative 1 what? It's really negative, whoops. It's really negative 1 of these tiles. So the way I'm going to write it is just negative 1 xy. We don't need that negative sign, so just a negative xy. All right, it's your turn. So grab some paper, copy these out, and you're going to do each one. Again, ask yourself how many different types of like terms do I have, and you might want to underline them with different kinds of underlines. Once you think you're done, come on back. I will reveal the answers one by one, so you can always do question A and then unpause. I'll do A, I'll give you a chance to pause it again. You can do B, blah, blah, blah. Okay, so here's our answer to A. Okay, hopefully you got it right. If you didn't, just remember that there is that invisible 1 here. So you're going to do 2x's plus 1x, and that's why it's a 3 and not a 2. I'm going to open up part B, so if you haven't done it yet, pause the video now. Okay. So with this question, there were 3 types of like terms, and that's why we have 3 different terms in our final answer. If you got this wrong, again, just go back to integers. If you've watched my integer video, this is just, I woke up one day with a debt of $4. Someone says, hey, you owe me one more. And so I'm now in debt 5. Pause the video and try C. Come on back when you're done. For part C, you need to be able to see that there are 2 different types of like terms. There are the like terms that are x squared, y squared. So thinking about the tile analogy, each tile would say x squared. And then you have, x squared, y squared. And then you have the set of like terms that are the xy's. So let's take a look at the x squared, y squared terms. If I did some rough work over here, this is what I would get. Now, when you don't have a visible number in front, so if you don't see a coefficient, that coefficient is an invisible one that usually doesn't get written down. So what this means is we have 2 tiles that say x squared, y squared, and we're going to take away 1 tile that says x squared, y squared, leaving us with 1 tile that says x squared, y squared. Now, we don't need to write this one, so when we're fully simplifying it, we do typically like to just leave it as this. So that's where this part of the answer came from. So in your working, if you have a 1 here as your final answer, you're not wrong. We just like to take that out when we're doing our final answer. Looking at the xy family here, I'm going to do a bit of rough work down at the bottom. I have positive 4xy. Take away 3xy, and again, what does that mean? It means we had 4 tiles that said xy's on them, and we're taking away 3 of those tiles. So I'm going to deal with the integers. 4 subtract 3 is 1, and what does it say on the tile? xy. And once again, we don't need that 1 here, so I'm going to get rid of that, and that's how I end up with this answer here. So again, if your final answer had a 1 here and a 1 here, you are correct. Just for proper math form, we like to take out those ones because they're not needed. So hopefully you got all of those right. Another thing I would suggest is putting stars beside any of the harder examples that we went through together. That way, if you are using this for notes, and this is something I would encourage you to do in your own classroom, you can easily go back to those specific examples when you're reviewing for tests and quizzes. And just a heads up, we are going to talk about how to add and subtract polynomial expressions like this, but that's going to be in a future video. If you found this video helpful, please like and subscribe.